So now we come to the last of our simple one-dimensional like solutions of the Schrödinger equation. It's a little more technical than the others, so the details are left to the homework problems. But let me sketch the solution of the one-dimensional tunnel junction. So this is an arrangement in which we have a region of allowed propagation of free electrons on the left up to x equals 0, then a change in potential to a potential that exceeds the electron's kinetic energy, so the electron is classically not allowed in this region, and then the potential drops again so that the electron is allowed again as a plane wave. This is a model for a scanning tunneling microscope, for example, where this would be a metal, this would be a small gap, and this would be a second metal, and we're going to ask the question, what is the probability that an electron propagates from this side of the gap to this side of the gap? When we write down the piecewise trial solutions for this situation, we have to allow for the probability that an electron is reflected at x equals 0. So we have an incident and a reflected wave with a amplitude reflection coefficient little r, r squared being the intensity or probability of reflection. Then we have these coefficients a and b for a exponentially decaying wave propagating this way. If an electron is reflected at this barrier, so it's now moving in the minus x direction, the corresponding exponential decay term is given by this term here. And finally, we have the term that the electron again propagates outside of the barrier with a coefficient t for the probability amplitude, t squared being the transmission. Now, to set this problem up, we have to use the boundary condition that psi of x and its derivative is continuous at the two boundaries. So we have here 1, 2, 3, 4 unknown coefficients, but we have 4 boundary conditions. At x equals 0, we want the wave function and its derivative to be continuous, and at x equals L, we want the wave function and its derivative to be continuous. If we use all of these boundary conditions together with the 4 equations just shown on the previous slide, and we solve for this coefficient little t and then square it, we end up with this expression here. It's quite a complicated expression. This here is the hyperbolic sign of kappa L, where kappa is the usual 2me minus v over h bar squared. Now, if we take the approximation that the barrier is thin, in other words, that 2 kappa L is much greater than 1, or rather the barrier is large, I'm sorry, that 2 kappa L is greater than 1, in other words, that we can in effect ignore the reflection inside the barrier, we finally end up with the result that the transmission probability decays exponentially, and so this means that the current across this gap, if we were to apply a voltage across it, would also decay exponentially. And interestingly, if we use V0 minus E, if we replace the difference between the electron's kinetic energy and the top of the barrier with this term psi, or phi rather, the work function of the electron, in other words, the energy required to remove an electron from the metal, we end up finally with this expression that the current decays exponentially with a decay length that is approximately 1 times the square root of the work function of the metal times the barrier gap in angstroms. Now we will calculate absolute values of current across tunnel junctions in chapter 7 of this book. It's actually quite easy to do this, but take it for now that measurable currents are obtainable across barriers of a few angstroms. What this expression tells us is that for the work function, being on the order of 5 electron volts or so, the current is going to decay by something like a factor of 10 for each angstrom that the barrier is increased. This phenomenon is the basis of the scanning tunneling microscope, a device in which a very fine metal probe is held a distance of a few angstroms above a surface by a piezoelectric scanning module, such that tunnel current can be driven between the metal probe and the metal surface. And because of this incredible sensitivity of current to distance, if the probe is moved, the current varies enormously if the height of the surface varies by even a fraction of a height of an atom. So by sensing these current changes as the probe is scanned over the surface, one can map out a surface with atomic resolution. This here is a scanning tunneling microscope image of a circle of iron atoms moved using an STM tip on a very cold nickel surface to form this beautiful structure in which the wave-like pattern you see inside this circle of iron atoms is actually an image of one of the allowed eigenstates of the electrons inside this circular confining potential. So what a wonderful irony. The quantum mechanical phenomenon of tunneling is used in the tunneling microscope to image quantum mechanics directly.